The speed differential between solid-state drives, SSDs, and dynamic random access memory (DRAM) is striking, with DRAM exhibiting speeds approximately 3,000 times faster than SSDs. This significant disparity in speed is crucial for the efficient processing of data within computer systems. The inherent structure of DRAM confines it to temporary storage, in contrast to the long-term storage capabilities of SSDs. This fundamental distinction underscores the unique roles each type of memory plays in enhancing overall computer performance. Numerous optimizations, such as burst buffers and folded DRAM layouts, have been developed to enhance data transfer speeds. These technological advancements are vital for improving the performance metrics of contemporary computing devices. The discussion in the video encompasses the architecture of DRAM modules, particularly highlighting the arrangement of memory chips and their interactions with the central processing unit, CPU, via memory channels. This structural design is imperative for ensuring data transfer efficiency. A comprehensive overview of the internal organization of DRAM microchips is provided, emphasizing the intricate nature of memory cells and the addressing mechanisms employed to access data. This elaborate structure facilitates high-capacity storage solutions. The manufacturing process of DRAM chips is meticulously examined, illustrating how sophisticated semiconductor fabrication techniques yield billions of memory cells on silicon wafers. Understanding this manufacturing process is essential for grasping the technological foundations of modern computing. In a 1T1C cell configuration, the capacitor is specifically designed to store a single bit of data by utilizing electrical charges to signify binary values. A thorough understanding of this component's construction is integral for comprehending the principles of memory storage. The access transistor plays a pivotal role in linking the capacitor to the bit line, thereby facilitating both data writing and reading operations. The precise regulation of this transistor is critical for ensuring the proper functionality of memory cells. Data refreshing becomes a necessary operation due to electron leakage occurring within the minute components of the memory cell, thus guaranteeing that stored information remains intact over extended periods. This refresh process is vital for maintaining data integrity. The process of data retrieval in DRAM commences with the activation of a row, which allows the capacitors to influence the bit line voltage. This change is subsequently sensed and amplified, thereby ensuring accurate data retrieval from the memory cells. Writing data in DRAM necessitates the use of more robust write drivers to override pre-existing charges within capacitors, thus ensuring precise data storage. This writing process is fundamental to preserving data consistency during operational activities. The act of refreshing memory cells is critical, particularly in light of charge leakage within miniature transistors. This refresh operation is performed at regular intervals, approximately every 64 milliseconds, to prevent data loss and entails a systematic recharging of the cells. The concept of row hits enables expedited data retrieval by bypassing the row opening process altogether. This efficiency is essential for optimizing the performance capabilities of the CPU. The design of DDR5 DRAM, featuring 32 banks, significantly enhances the likelihood of row hits by permitting simultaneous access to multiple rows. This capability effectively reduces the time required for data access. The implementation of burst buffers facilitates rapid data transfers, thereby enhancing the efficiency of both reading and writing operations. This design optimization is instrumental in enabling the effective processing of extensive data volumes. Segmenting large memory arrays into smaller blocks leads to increased efficiency and faster access to the data contained within each subarray. This design strategy is particularly crucial for optimizing the performance of modern DRAM. The utilization of cross-coupled inverters generates differential pairs that bolster noise immunity while reducing parasitic capacitance. Such optimizations contribute to superior signal amplification within the memory system. The precise timing of address and command signals is vital for the effective operation of DRAM. However, this topic was not explored in depth due to time limitations. Nonetheless, a comprehension of DDR and SDRAM remains essential for understanding contemporary memory technologies.